So a couple of days ago, I stumbled across this repository called Hacker Laws. So what this is basically just a big README file with a bunch of laws and principles related to software engineering. There's a ton of them. I've gone through all of them, but in this video, I wanted to share the ones that I find the most interesting and insightful. The first one is the 99-1 principle, or the 1% rule. It states that the 99-1 principle suggests that within an internet community such as a wiki, 90% of participants only consume content, 9% edit or modify content, and 1% of participants add content. And a real-world example, a 2014 study of 4 digital health social networks found that the top 1% created 73% of posts, the next 9% accounted for an average of 25%, and the remaining 90% accounted for an average of 2%. And I think this is probably true in most social media, YouTube, Instagram, whatever. And I know for myself, I've been an avid consumer of content online for many years now. And I want to try and be part of the community that actually creates content as well. I think it's valuable to share what you're thinking, share your thoughts on certain subjects. It helps you overcome fear and procrastination. And perhaps it's something that you should try and do more of moving forward as well. The next one is called the broken windows theory. And the broken windows theory suggests that visible signs of crime or lack of care of an environment lead to further and more serious crimes or further deterioration of the environment. This theory has been applied to software development, suggesting that poor quality code or technical debt can lead to a perception that efforts to improve quality may be ignored or undervalued, thus leading to further poor quality code. And this effect cascades, leading to a great decrease in quality over time. This probably hits home for many of you, myself included, definitely. And this is something that I've been bringing up, this actual theory, in a number of projects or companies that I've been in the past. It suggests that we should actually care about the code that we commit into the main or master branch of whatever we're working with. So if you try to do that along the way, you care about the quality of the code that you're committing, you want to make it as good as possible, you don't want to rush things, because in the end, if you do, you end up with a ton of suboptimal or half-broken or hard to understand code, which eventually then leads to proving this theory correct, that once the code base reaches a critical point of this is just a big mess now, you're not going to care about the next piece of code that you want to submit into it. And it's just downhill from there. So we want to care about the quality of the code that we write in the project that we're working on. Next up is Brooks' Law, and this is going to be a classic for many of us here as well. So adding human resources to a late software development project makes it later. This law suggests that in many cases, attempting to accelerate the delivery of a project, which is already late, by adding more people will make the delivery even later. Brooks is clear that this is an oversimplification. However, the general reasoning is that given the ramp-up time of new resources and the communication overheads, in the immediate short-term velocity decreases. Also, many tasks may not be divisible, for example, easily distributed between more resources, meaning the potential velocity increase is also lower. So this is something that you may recognize from your own career. Maybe you've been on a project that is running late and management thinks that it's a good idea to let's just double the amount of engineers and double the speed and we'll get done in time. As Brooks' Law states, and as many of us know, that it's not going to work that well. This next one is going to be a two-parter. First, we're going to look at Hofstadter's law, and then we're going to look at Parkinson's law, and hopefully draw some conclusions out of the two. So first up, Hofstadter's law states that it always takes longer than you expect, even when you take into account Hofstadter's law. which is kind of funny because this would be a recursion, I guess. You apply Hofstadter's law, but then you've applied it, you have to apply it again, and the estimate just kind of skyrockets from there. You might have heard this law referred to when looking at estimates for how long something will take. It seems a truism in software development that we tend to not be very good at accurately estimating how long something will take to deliver. So let's keep this one in mind. And let's quickly also look at Parkinson's law right here. So Parkinson's law states that work expands as to fill the time available for its completion. So in its original context, this law was based on studies of bureaucracies. It may be pessimistically applied to software development initiatives, the theory being that teams will be inefficient until deadlines near, then rush to complete work by the deadline, thus making the actual deadline somewhat arbitrary. If this law were combined with Hofstadter's law, the one that we just looked at, an even more pessimistic viewpoint is reached. Work will expand to fill the time available for its completion and still take longer than expected. So, how do we account for this when we are estimating or trying to complete projects or certain tasks? Because we will have to give estimations on certain tasks. And as we just saw with Hofstadter's law, even if we do that, we apply Hofstadter's law, we add some extra time, we know from Parkinson's law that the work available will just kind of fill up that time. So to address part of the problem here, I think it's important that when faced with implementing a certain feature or a project or a task, whatever it might be, you should try and figure out an MVP, a minimal viable product. So what's the simplest version of this feature that you're trying to build? And then try to build that one first. So build the simplest version, make that complete, maybe even integrate it into your system. And then from there, you can keep adding certain things to it, certain nice to haves, and build up on that. So in trying to do that, hopefully you will be able to have something that is at least viable and working and fills the must-have requirements, and being able to do that within a reasonable amount of time. So this comes into keeping things simple and trying to build the simplest version of a thing first before thinking about all of the features that you may need to add. Speaking of simplicity, this is going to be somewhat of a theme, I feel like, in this video. Next up, we have Kernighan's law. So this one says that debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. So Kernighan's law is named for Brian Kernighan and derived from a quote from Kernighan and Plauger's book, The Elements of Programming Style. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? While hyperbolic, Kernighan's law makes the argument that simple code is to be preferred over complex code, because debugging any issues that arise in the complex code may be costly or even infeasible. Now, this hits home for me quite a bit. And it's something that I think a lot about in my current work and in previous work as well. I think for myself, when I was younger and more junior, being clever in your code was attractive. You wanted to write something that looked cool and looked kind of complex and fancy. And like, hey, I figured something out and now I can't really understand it. And that felt like an accomplishment. And over the years, I've come to value, as many people that I'm working with, value simplicity much, much more. And I think it's important here that we think about when we write code, we are actually writing it for other humans to read. So not only debugging is much harder than actually writing the code itself, coming back, like even a week after or a month after, and reading and reasoning about the code that you wrote is often harder than writing it in the first place. So we should try and not be too clever, not be too fancy in the implementation of our projects, but rather write as simple and as clear code as possible. Next up is the Law of Triviality. And this law suggests that groups will give far more time and attention to trivial or cosmetic issues rather than serious and substantial ones. The common fictional example used is that of a committee approving plans for a nuclear power plant, who spend the majority of their time discussing the structure of the bike shed rather than the far more important design of the power plant itself. It can be difficult to give valuable input on discussions about very large, complex topics without a high degree of subject matter expertise or preparation. However, people want to be seen to be contributing valuable input, hence a tendency to focus too much time on small details which can be reasoned about easily but are not necessarily of particular importance. The fictional example above led to the usage of the term bike shedding. Really? I had no idea. All right, cool. Yeah, the term bike shedding as an expression for wasting time on trivial details. Okay. A related term is yaw-shawing, which connotes a seemingly irrelevant activity that is part of a long chain of prerequisite to the main task. I've been guilty of this in my professional time. I feel like the law of triviality, and it's something that I've been noticing a lot as well, in my work, in myself, as well as in others. And I think there's a piece here that is probably, it's down here. People want to be seen contributing. And you find things that can be reasoned about easily. So if you're in a big, complex project, which is very hard to understand the core structure of it, or the most important integrational parts of the project itself, it's much easier spending time with kind of surface level trivialities and fixing little things here and tweaking little things at the top of the complexity chain, so to speak. So what I take with me with this one is, I guess, noticing in myself when I'm doing this, and actually trying to take the time to wrap my head around and address not only trivial issues, but more complex and more substantial issues. Next up, we have the 2 pizza rule. So this is from Jeff Bezos. If you can't feed a team with 2 pizzas, it's too large. So this rule suggests that regardless of the size of the company, teams should be small enough to be fed by 2 pizzas. Attributed to Jeff Bezos, attributed to Jeff Bezos at Amazon. This belief suggests that large teams are inherently inefficient. This is supported by the fact that as the team size increases linearly, the links between people increases quadratically. Thus, the cost of coordinating and communicating also grows quadratically. If this cost of coordination is essentially overhead, then smaller teams should be preferred. And then we have some fancy graph here of these blue dots here are the people, and then the connections between the people are these black lines. This one makes a ton of sense to me as well. I've been working in both large companies and small companies, small teams and large teams. And I think, how many people can you feed with 2 pizzas? For me, like 4 or 5 people can be reasonably fed with 2 pizzas. Once you go to 6 and beyond, 2 pizzas might not be enough anymore. I've been in much larger teams, and I think actually if you if you're in a larger team, let's say 10, 12 people, a solution to this, I think, is you have to kind of split things up in the team. You want to be a coherent team, you want to collaborate with each other, but everyone can't be involved with everything all the time. You have to give smaller groups of people kind of an isolated responsibility of certain initiatives or features or whatever it might be. And then fine, you communicate and collaborate in the broader team as well. But that, I think, is a reasonable solution perhaps to this problem. If you're in a larger team, trying to find ways to create temporarily subsets of teams within that larger team, and keeping the size of the sub-team to 4 or 5 people. Okay, this next one is a short one. It's Wheaton's law, and it's simple. It's don't be a dick. But let's read through the description here as well. Coined by Will Wheaton, Star Trek, The Next Generation, The Big Bang Theory, this simple, concise, and powerful law aims for an increase in harmony and respect within a professional organization. It can be applied when speaking with coworkers, performing code reviews, encountering other points of view, critiquing, and in general, most professional interactions humans have with each other. Not much to say here, I think, but keep this one in mind, both in your professional life and in your personal life, in the interactions that you have, and don't be a dick. Okay, this next one is going to be a two-parter as well, and you may have heard of both of these rules. The first one is the dry principle. So every piece of knowledge must have a single, unambiguous, authoritative representation within a system. So DRY is an acronym for Don't Repeat Yourself. This principle aims to help developers reducing the repetition of code and keep the information in a single place, and was cited in 1999 by Andrew Hunt and Dave Tommans in the book The Pragmatic Programmer. Great book, by the way, that I wish I had read earlier in my career. I read it for the first time last year, but super valuable, I think, for both junior and very senior engineers alike. Great book. The opposite of dry would be wet. Write everything twice, or we enjoy typing. Okay. In practice, if you have the same piece of information in 2 or more places, different places, you can use dry to merge them into a single one and reuse it whenever you want or need it. So I think this last sentence here really hammers in how you should use dry. If you're in a huge code base and you have certain pieces of logic that is in many, many places, which is identical or more or less identical, yes, it makes sense to break that out, put it in one place, and then have all of these different places or apps or whatever use that centralized place. But let's move on and look at the second kind of related one, which is the KISS principle. KISS stands for, keep it simple, I guess with one S, but if you want to do both S, it's keep it simple, stupid. The KISS principle states that most systems work best if they are kept simple rather than made complicated. Therefore, simplicity should be a key goal in design, yes. And unnecessary complexity should be avoided. Originating in the US Navy in 1960, the phrase has been associated with aircraft engineer Kelly Johnson. Okay, I'm actually going to stop here and just keep it at this. So, dry versus KISS. We've already established that, yes, it makes sense to, if you repeat yourself in multiple ways across the code base, just put the piece of logic in one place and then use it in the other places. What I've encountered now and then in my experience, in my profession, is that we're too afraid of repeating ourselves. So you might be working on a single piece of logic in a single file or something, and you type out the solution or you iterate on it or whatever, and eventually you found out that you find yourself repeating certain things a little bit, perhaps. If you are really into the dry principle and you hate repeating yourself, you will always think about ways to abstract logic away. So rather than having these things here kind of similar in a couple of places, what if we create a new piece of function somewhere that we can use and we can have some kind of abstraction over this and reuse it? Oftentimes it comes into conflict with the keep it simple principle. And for me, what I found in myself that sometimes it's okay to repeat yourself a little bit here and there if it keeps things simple enough. And then eventually, fine, if you realize that this is going to have to repeat over and over again in other areas of the code base, break it out and make something general out of it. But oftentimes, dry comes at the cost of keeping things simple. And in the end, like we touched on earlier in this video, keeping things simple and readable and reasonable is, in my opinion, more important than not repeating yourself all too much. Last up, we have YAGNI, which is also an acronym for you ain't gonna need it. Always implement things when you actually need them, never when you just foresee that you need them. So this is from Extreme Programming. This XP principle suggests that developers should only implement functionality that is needed for the immediate requirements and avoid attempts to predict the future by implementing functionality that might be needed later. Adhering to this principle should reduce the amount of unused code in the codebase and avoid time and effort being wasted on functionality that brings no value. So this one goes back a little bit to what we talked about earlier that was Hofstadter's law and Parkinson's law about trying to make a first MVP version of whatever you're building. Just do the simplest thing you can do, get the must-have requirements in there, and then if you need them much later, perhaps implement new features on top of it. So don't try to do everything at once. Keep it simple. Don't implement things that you don't need right now. Keep them fine, like in your notes or whatever, for later, but don't do everything at once. So this was the last law or principle that I wanted to share in this video. I'm really curious about your thoughts on this. If you read the article, it's linked in the description. If you think that I missed a really crucial law, or if you disagree with something that I said related to the laws or principles that we looked at, would love to hear it in the comments. And if you're still here and you enjoyed the video, consider giving it a like, maybe even subscribing to the channel. That would mean a lot to me. Have a great day.